You had a question? Okay. So the way the subject is developed is in analogy with electromagnetic waves, although we'll see that there are some differences. So we recall electromagnetic wave, okay, how we study electromagnetic wave. So this is just in flat space. So you have the equation. Okay, here now all indices are raised and lowered by eta because you are dealing with flat space time. So while studying electromagnetic waves, okay, one divides this problem into two parts. Okay. So the first part is that we set J nu equal to 0, no source, and study plane wave solutions. Okay. So if this is 0, then this is just linear equation, right? It's linear in mu, so you can find solutions easily. Okay. And the solution takes the form okay, where k dot x is again eta mu nu k mu x nu. Okay. With the condition that k square is 0 and k dot epsilon equal to 0. Okay, this is what is called the gauge condition. Okay, because you have gauge invariance, you can shift mu by a derivative, okay, gradient. Okay, you can use that gauge fixing to fix this. Okay. But this also has residual gauge invariance. Okay. Namely, epsilon mu is equivalent to epsilon mu plus lambda k mu, where lambda is any constant. This is in the Lorentz sketch, yes. I mean, you can easily solve it in Lorentz sketch because then it just becomes box mu equal to 0 and you can solve this. Okay, but at the end, the the representative of plane wave solutions, right? The gauge invariant part of that content is the same in all gauges. Okay, so for example, here, if you take k to be along the third direction, right? Suppose you take, if we take, okay, before we do that, let me first pause and see if it is familiar to everybody, right? So the idea that this epsilon is an arbitrary vector to begin with, but we impose the condition k dot epsilon equal to 0, right? That's the gauge condition, Lorentz gauge condition. And then if we also impose k square equal to 0, you can easily convince yourself that this solves this equation. Okay, because this equation is roughly box. Yeah, so let me write. So this is box nu minus so in the Lorentz gauge, you impose that this is 0, right? This becomes box mu equal to 0. Then in the momentum space, once you look for a solution of this form, right, the box acting on this gives you k square multiplied by k square. Okay, so that sets k square equal to 0. And then by demanding that the Lorentz gauge condition is satisfied, this condition, you get k dot epsilon equal to 0. Okay. But then you find that the original gauge freedom that we had, right, the gauge freedom was mu going to mu plus the total derivative. This in the momentum space corresponds to translating epsilon mu by epsilon mu plus k mu times some arbitrary multiple of k mu, right? This capital lambda, the Fourier transform I'm calling this small lambda. Now the point is that you might have thought that because you have already said gauge condition k dot epsilon equal to 0, right? You will not have any this freedom anymore, okay, because you have chosen a gauge. But that's not the way it works, because you can check that if k dot epsilon is 0, then k dot this is also 0, right? Because of the fact that k square is 0. So this is true on when the equation of motion is satisfied. So if k dot epsilon is 0, then k dot this is also equal to 0. So this is as good a choice of epsilon as the original epsilon. But these are equivalent because they are just related by gauge transformation. Is summit is? No, it comes from equation of motion, right? We ask for mu equal to epsilon into the ik dot x. You can always do a Fourier decomposition, right? Once you have demanded that, once you have taken this form, right, then these just follow from the equations of motion and gauge. Okay, and then we recall that we had this gauge invariance under this, right? We had fixed this to impose the equation of motion, but then we find that after you have solved the equation of motion by setting k square equal to 0, right, the gauge is not fixed. You still have the freedom of translating epsilon by a term proportional to k mu. So that means that this fixes, so to start with, epsilon had 4 components, right? Because it's a 4 vector. K dot epsilon equal to 0 makes it 3 components, right? 1 condition on 4. But this one tells us that there is another equivalence between different choices of epsilon, right? Which is parameterized by this lambda. So using that, you can remove 1 more component. Okay, so effectively, the number of independent components of epsilon is 2. So just as an example, if we take k as k 0 0, let me call this some p 0 0 p, okay, which means it has it only moves, the vector is directed on the 3rd direction in space, and of course then this is fixed because of the k square equal to 0 condition, right? K square is k0 square minus k0 square plus k3 square. So if we take it to be this, then the independent choice we can take epsilon to be either 0 1 0 0 or 0 0 1 0, because these satisfy k square equal to 0 have already satisfied. These satisfy that epsilon dot k is 0, right? Because this has components in the 0 and 3 direction. This has components only in the 1 and 2 direction. And once you have gotten these 2 solutions, we know that you have got everything, right? You could have in principle added to any of these some arbitrary function, arbitrary multiple of k, arbitrary multiple of this vector, okay? But that will give exactly the same polarization, right? Because that's gauge equivalent to what we had started with. Yeah, the point is that if you take any other k, right, you can always orient your axis so that the direction of k, the spatial direction of k is along the 3rd direction, right? See, once this part is fixed, right, then this is already fixed because k square equal to 0 tells us this is equal to mod of this, right? And fixing this, you can always choose your axis because you have rotational invariance, right? You can choose your axis so that it's along the 3rd direction. So it's in a sense more general. If you want to go to another frame, you just have to rotate this whole thing. right? Rotate both k and then epsilon. Well, at the end, right, after you put all the constraints, you will be left with two independent components. Okay, that is always the case, right? And then you can ask in different gauges how that arises, right? But the fact that you will be left with two independent components, that's a gauge invariance. This is in the plane wave. This is in absence of matter, right? Yeah, so if you do have matter and sources, right, you don't try to study waves in that background, right? Because then it was very hard to distinguish which part is wave and which part is electrostatic, right? You always talk about waves away from the matter, right? There may be some matter that is in some region, right? It may produce some wave, but at the end, you look at the region which is far away, and then there you can identify the propagation of electromagnetic wave. So that is the step 2, right? The step 2 is that given some source, typically we need time dependent source. We solve the full equation. And then study the form of mu far away, where J mu is 0, right? Imagine that the source is confined in some region, right, where say a lot of charged particles are oscillating, right, or moving around. So this gives the source, right? Using this source, you just solve this to find what f mu is everywhere in space time. And then you study this far away, okay, where this is 0, and there we can express mu as a superposition of plane waves. And express this as superposition of plane waves to find electromagnetic radiation. Yes, if you want to know, if you have a set of moving charges, right, and you want to know what kind of electromagnetic radiation you have, you first calculate, solve this equation, but then you look at the solution far away. Okay? And far away from this, right, if you express the field strength, you can write it as a linear combination of plane waves, and that tells you what kind of electromagnetic radiation is coming out of the sources. Yes, relative polarization, how much is the amplitude, right? Because the strength of epsilon, right? How big epsilon is, right?
I mean, far away it will always the proportion will be some linear combination of those two.
Exactly. But those two modes, the k can vary, right? K is a vector. Right. So it will be, in general, it will be linear superposition, right, of all k, right? It will involve an integral, right? But then, I mean, typically you can guess it from the, intuitively, but you can also prove it, that if you are looking here, for example, suppose the source is localized here, right? Then in this region, you can approximate the field by a set of plane waves coming in this direction. Okay, because that's intuitively you see that the radiation should come from there, right? So it better be that the radiation is moving around in this direction. Okay, and that's what you can show, that that is dominated by k along this direction. Similarly, here the k, it will be some k in this direction, okay? But the strength can depend on the angles, right? or the magnitude of k. Okay, so epsilon mu will typically be a function of the magnitude of k and also the theta and phi, right? The direction in which you are looking. So all that information will be contained in the source. Yeah, it is okay. You can think of this as scattering problem, but I am thinking of it as a localized source problem. Right? Imagine that there is a set of charged particles, right? Set of molecules are interacting, right? The electrons and protons inside the molecules are moving, right? So that will produce some electromagnetic radiation, right? And that's what you are trying to study. So you are not throwing in some molecules and taking out some molecules. That also you can do. Right? It's a little more complicated problem because the source is not localized. But as long as you are away from the source, you can use this inside.
What do you expect to see at that point?
Yes. Yes. Well, the point is typically. Yeah, but I'm assuming the source is localized here, and you have gone very far away, right? Then you will see that the radiation is coming from this direction. Yeah, but this means epsilon will be 0 in those cases, right? But the k, as long as you are sufficiently far away, right, the k that we'll see, right, will be along the direction of the line of sight. Right? That's all I am saying. This is not something which is obvious, right? Because in principle, you could have when you calculate here, right, you may find a k that's correspond to this vector, right? Okay. But that doesn't happen. You can prove this, right, just from this formula, right? You don't need any further insight. Okay? Just by solving that formula, you can prove that the line of the k that we'll see will be along the line of sight. Okay, and I mean you can understand it easily if you use a quantum intuition, because if it's coming because a set of photons are being emitted from here, right? K is roughly the momentum of the photon, right? Up to scaling by h bar. So it better be that the photons are coming from here and reaching here, right? So the photons momentum should be along this direction. Okay, otherwise it will be very hard to interpret this result, right? Classically, you can say, okay, you see this here, you get all k, right? But that classically, that k doesn't necessarily reflect anything about the momentum of a particle. So okay, you can say, well, it may come with a k correspond to this line, right? But that will be very hard to interpret in a quantum theory, right? That will mean that there are some particles that are coming with some momentum corresponding to this direction, right? If the source is localized here, that seems intuitively not correct, right? And but at the end, everything works out fine, right? And you do see that what you see, the k that you see from here is along this line of sight, right? Provided you go far away, right? This is in the R goes to infinity limit.
What is the problem in interpreting these solutions with sources?
What is the problem?
In interpreting this, because we are always going far away from.
Yes, but suppose here, right, you find that you are receiving some electromagnetic radiation which has k that corresponds to a vector directed in this direction, right? So now those k's, right, in quantum theory, we'll think of those as photons carrying that momentum along those directions, right? So that means as if there are photons coming from this direction, right? That sounds counterintuitive, right? If the source is here, right, if the photons better be omitted from the source, right? So what I'm saying is, if you had found that here you find k that is coming from this direction, right? You can also think of it classically. You don't have to go to quantum mechanics. If you look at the momentum that's carried by the electromagnetic wave, right? That's also proportional to k. That direction is fixed by k. So you can think in an electromagnetic wave, right? If you find an electromagnetic wave that has k along this direction, right? That means you are receiving some wave which has momentum directed here in this direction, right? Again, that's counterintuitive, because if the waves are being emitted from here, right, how can it carry momentum that is in this direction? Nearby, of course, everything is complicated, right? You shouldn't try to use this insight near the source. Okay, but far away from the source, you can use this intuition. But and as I said, this comes out of the Maxwell's equations. Okay, it's not something that you have to assume. When you solve this, you do find that the wave is directed. Okay, now our goal, of course, is not to do electromagnetism, right? This is just an analogy. Okay, we want to study the analog of this in gravity. So let's try to proceed as in electromagnetism. So you have R mu nu minus half R G mu nu equal to H by G T mu nu. Okay, where T is the sum of everything, okay? Matter, electromagnetism. So the naive guess would be, okay, that if you try to follow the same strategy as electromagnetism, that you ignore this term, the source term. Okay, so ignore source term. And solve. And then step 2 would be study the effect of sources. But here the first step itself has to be modified. And the reason that it has to be modified is because this is not linear. It's a R mu nu is a highly nonlinear function of the metal. So we cannot really solve this and get plane waves, right? We cannot superpose solutions of these equations. So the strategy that one follows is to linearize it. Okay. So we need to linearize it. We need to linearize this equation, and I'll explain what I mean by linearize. So we take G mu nu equal to eta mu nu plus H mu nu and take H mu nu to be small. So you can calculate R mu nu. I'll write this as R1 mu nu plus higher order terms. Okay, let me write K mu nu, call this something. So this is the term that is linear in H mu nu. Okay, we'll calculate what this is. Okay. But if you just recall the expression for the Riemann tensor, right, you will see that there is a term that is linear in H. Because Riemann tensor is that there are several kinds of terms. One is derivative of gamma, right? Antisymmetrized. And then there's gamma gamma. Okay. Gamma gamma term is always quadratic in H because gamma is linear in H. Right? Gamma inverse derivatives for a metric. So gamma gamma term we can ignore, right? At this for calculating R1. But the derivative of gamma is a term that is linear in H, right? Because gamma is linear in H. So those are the terms I'm calling R1 mu nu. Okay. Anything else we are calling K mu nu. So this is higher order terms. Now R is G mu nu, R mu nu. This I can write as eta mu nu plus something. You have any idea what the something is? If you want to, G mu nu we have taken to be eta mu nu plus H mu nu. No, first I just want to write G mu, G upper mu nu, right? In terms of this. Yes. Yeah, but we want to write in terms of H, right? So suitable contraction of 2G, so you have to raise our index again, right? That's what you are trying to figure out. Right? Yes. For the linear term, but I'm just trying to write the whole thing first. Then we'll separate out the linear term. Okay. So the point is, if G is this, right, you can write this as G as eta plus H as a matrix, right? Okay. Which you can also write as eta times 1 plus eta inverse H. So G inverse is 1 plus eta inverse H inverse times eta inverse. So which you can expand out, right? Because H is small, 1 minus eta inverse H plus eta inverse H minus, it goes on, times eta inverse. Okay. So this is eta inverse minus eta inverse H, eta inverse plus eta inverse H, eta inverse H, eta inverse, and so on. Yeah, so the point is that G upper mu nu has an expansion in parts of H, okay, which you can calculate, and after any order that you want to calculate, you can calculate. Okay, it will not be needed immediately, but it will be needed later, right, for something that I'm going to say. Anyway, so this is eta inverse is as eta upper mu nu, right? So you can write it that way. So it is eta upper mu nu plus terms of order H times R1 mu nu plus K mu nu. Okay, so the linear term, this is already linear in H. Okay, these are quadratic and higher order. So these terms are not relevant for calculating the linear term in this expression, right? So this I can write as eta mu nu, R1 mu nu, plus anything else I'll call L. This contains quadratic and higher powers. So then this says that the source-free Einstein equation, source-free Einstein's equation we can write as R1 mu nu minus half R1. Okay. This is what I want to call R1. G mu nu is eta mu nu plus H mu nu. Yeah. Is equal to plus K mu nu minus half L G mu nu equal to 0. H times R1, yes. This one, here, these terms. That's quadratic, right? The R1 is already linear, right? So that will be quadratic. That's all dumped into L. Okay. So the algebra is complicated, but the important point that I'm trying to emphasize, in principle, you can calculate L. Right? Why you want to calculate L will become clear a little later. Okay, but in principle, you can calculate L as a function of H, right? Just by doing this manipulation. So this I can write now as R1 mu nu minus half R1 eta mu nu equal to minus half R1 plus half R1 H mu nu minus K mu nu plus half LG mu nu. Is this clear? So I have just rewritten Einstein's equation. I have not done anything else, right? And I have rewritten it in such a way that the left hand side involves only terms linear in H mu nu, and right hand side is quadratic and higher order in H mu nu. Okay. So now we can also put back the source. Okay, if we have source, we also add to this 8 pi gt mu nu. Right? It doesn't cost anything to add back the source, right? Because all we started with this equal to 0, but if we had an 8 pi j t mu nu, we just add it here. No, I have kept the linear terms on the left hand side. Everything else I have brought to the right hand side. Well, if you assume that the source is localized, right, it will of course change the background metric, but only near the source. Right? Far away, we expect it to be flat space. That's I have not assumed necessarily. Yeah. So what you are saying is that near the source, H mu nu may not be small, right? Okay, H mu nu let it be large, right? This is still valid, right? Except that this is you have said how to expand in powers of H mu nu, right? That may not be valid, but you can write on exact expression also, right? Just isolate whatever is linear and then everything else you dump into the right hand side. Well, the question is how small, right? So let's keep them, right? Eventually will drop, right? But with some, I'll explain what is the significance of these terms, right? That's why I've kept this. Well, we exist, so that is certainly possible, right? I mean, no one linearizes for us, right? So there are certainly solutions possible, right? I mean, it's a question of how easy it will be to find it, right? And people do solve Einstein's equation numerically, right? The full nonlinear equations. Analytical solutions are hard unless you have specific cases where there are symmetries and all, right? If you have a spherically symmetric source, you can probably solve it, but otherwise it's hard. Gravitational wave solutions, yes. Without linearization, yeah. Yeah. I mean, if you want to get something like a wave, right? We have to linearize it. Exactly. Yeah, but those are not the kind that you're asking for here, right? Those are very special, right? So in some very special cases, you can get nonlinear waves like solitons, but those are, in general, you will not have those. Okay, so now the idea is that the right-hand side, whatever appears there, okay, I'm going to write this, I'm going to give it a name. Yes. Yeah. So we'll not call that wave, right? We'll call something wave only far away. See, this is true also in electromagnetism, right? If you have a time varying source, right, close to the matter, right, it's hard to distinguish what is a wave and what is, for example, the part of the electrostatic field, right? Only far away you can distinguish, because the field strength for all the electrostatic or the static object, right, the electrostatic field strength drop off as 1 over r square, whereas the waves fall off as 1 over r, right? So they dominate at far away, and that will also be the case for gravity. Yeah, you're assuming that h mu nu is small, means that its derivatives are all finite multiple of h mu nu. So h mu nu and its derivatives are small. Yeah, I mean, if you have a delta function, for example, right, then it doesn't help. Yeah. Exactly. That's so there is an overall factor in front of h mu nu, which is a small parameter, right? And my multiplied by some smooth function. That's the kind of thing we're thinking of. Yeah, exactly. Yeah, times some smooth function. Well, the point is it's a question of what kind of system you are dealing with, right? The kind of system that you are dealing with, they have smooth h mu nu, right? So the derivatives are all finite, finite multiple of h mu nu, right? But of course, you can also consider cases where it's not the case, right? Near a singularity, for example, right? The derivative of h mu nu may be much stronger than h mu nu. But we are assuming here that you are in a situation where you have a smooth h mu nu and the overall factor is small. Okay, so now the point is that this quantity, I'm going to give a name, and that's 8 pi g. So T gravitational h mu nu is just 1 over 8 pi g times this, right? Some function of h mu nu. It involves quadratic and higher powers. That's all that is important. So this quantity is what is known as the gravitational energy bound temperature. This is something that you don't see for electromagnetics, because electromagnetic fields are linear, right? Electromagnetic fields do not source themselves, but gravity actually sources itself, because gravitational waves also carry energy, okay, as defined by this. So you can think of this as a gravity sourcing itself. right? Because everything carries energy, so gravitational waves should also carry energy, and that's what is responsible for this term.
Electromagnetic source does not source themselves.
Don't source themselves. If we just had pure Maxwell theory, right, without source, then it's completely linear, right? So there's nothing on the right hand side. If you write it as a linear plus non-linear term, there'll be nothing on the right hand side. Right? That's the meaning. That's the statement that it doesn't source itself, right? In the quantum version, right, the analog of this is that the photons are chargeless, right? Photon doesn't produce an electromagnetic field, even though the photons are carriers of electromagnetic field. Right? This is not the case for gravity, right? Gravitational waves also carry energy, right? And energy, as you know, is the source of gravity. Right? So non-linearity of gravity, right, can also be thought of it this way, that the gravity sources itself.
We have a source which is gravity.
Exactly. Exactly. That's right. Exactly. Right. For example, when two black holes merge, right, there is now no T mu nu outside the black hole, and whatever is inside cannot come out anyway, right? But gravity is non-linear, so there is a gravitational field outside the black hole, and that produces gravitational waves that we see. Right? If gravity didn't source itself, right, then when two black holes merge, right, there is no T mu nu that is visible to us. Right? There is maybe T mu nu inside, but that is not visible. Right? And as we have seen, Schwarzschild solution is a solution without T mu nu. So the reason that the black hole merger produces gravitational wave is because of this, that the gravity sources itself. Right? And that's this term. Whatever is this complicated term, that is responsible. Right? You can say, okay, if you can get some insight by keeping only the quadratic term. If gravity is not very strong, then maybe just a quadratic term is good enough, right? That's an approximation that you can start with. But eventually, when near merger, right, when gravitational fields are very strong, then you have to look at the full nonlinear term and solve this.
You just said that
Yeah, okay. Perhaps I mean that was not completely correct, because even though we don't see the energy momentum tensor distribution inside, right, we do see the masses, right? Because the information of the mass, as we have seen, right, is contained in this. Okay? So you can think of this as point sources, right? So in a T mu nu is a delta function source, right? You can think of it that way. So indeed, we do have some matter source, okay? But you also have gravity, right? Particularly when the black holes are close to each other, right? The gravitational source plays an important role. Sorry, maybe I didn't answer your question.
I was just going to ask you this question that since the RHS is by definition,
Yes.
far away from the source, this is not really sourcing the gravity.
Yes, true. But that's true even in electromagnetism, right? Because the source that is there can be localized, but it can produce electromagnetic force which is far away, right? So the fact that the source is localized doesn't mean that the electromagnetic field is localized, right? Because that propagates.
So its importance is
exactly. Its importance is basically in the near zone, right, where the gravity is strong. Right? That's why the nonlinear effects are important. So the one way you can model this collision of black holes, okay, this is assuming that it's spherically symmetric. Otherwise, you have to use this Kerr solution. That you have these 2 point masses, okay, which are rotating around each other, which produces some source. If you think of this point mass, there is delta function source, okay? And then that has its own gravitational field, okay, which becomes stronger and stronger as the masses come close together. Okay? And then it's the combined effect of those point sources as well as the gravitational field that acts as the source for gravitational waves. Okay, that's why you need to keep track of these nonlinear terms. No, mass cannot be shielded, right? That we have discussed, right? The charge and mass cannot be shielded. Exactly. Exactly. You can just think of the point mass.
But heat contributions will not be visible from beyond a certain radius.
Exactly. That's right. Right. So basically, you think of them as point mass, and then whatever the gravitational field is doing outside the horizon. What it's doing out inside the horizon is of no relevance. Well, there is a way to define horizon, right? I mean, basically, it's a surface which acts as a one-way membrane. That once you go in, you cannot come out.
So as these two sources evolve, this surface that you're talking about will change in time.
Yes, indeed, exactly. Right? And eventually, you have one horizon instead of two. Gravity. Yeah, it does. Okay. In fact, it does it in a somewhat better way, right? Let me explain what relation it satisfies. Yeah. But Einstein's tensor satisfies a better relation than what we had earlier. Let me explain what you may have better. Okay, you may not call it better, but more convenient relation, right? Let me put it that way. So the point is that the exercise, okay, in fact, the exercise will be almost immediate from based on what I'm going to do later, okay, because I actually calculate R1 value, that this relation is true. So now this is raised by eta, and it's an ordinary derivative. If you remember that when it was a full R mu nu, right, and when eta mu nu was G mu nu, there is a similar relation, but this was G and this was covariant derivative. But this relation also holds. Okay, once I calculate R1, it will become trivial that it holds. Okay, but you can check that indeed this relation is true, right? Which means for consistency, you see on the right other side that eta rho mu so this is ordinary conservation law. Okay, as if you are having an energy momentum conservation law in flat space time, right? Because indices are raised and lowered by eta, and this is ordinary derivative. So this combination satisfies the ordinary energy momentum tensor conservation law. Okay, as if we have no curvature in space time, right? Because the effect of curvature, etc., has already gone into the definition of T gravitational. So it is in that sense, okay, I don't know whether you can call it better, but it's certainly more convenient, right, to use this than the ones with covariant derivative. Yes. Yes. Yeah. So T mu nu contains some G inside, if that's what you mean, right? Yes. So that's there. No, I'm not doing an order by order analysis. This is exact. So far, there is an approximation, right? I've just read it in the original thing in this form, right? The T mu nu, see that R1 sorry, are not R1. The K mu nu L, etc. can contain arbitrary high power of H. Right? I have not assumed anything. I have just taken rearranged things so that the linear terms go on the left and everything else go on the right. This one. Oh, we'll write the expression for R1, it will become clear. Right? It's basically the linear version of the general Bianchi identity. Right? You can think of it that way. If you take the general Bianchi identity, that's an identity, right? You just expand this in powers of H mu nu, and so it should hold for every power in H mu nu, right? And the leading term, the linear term, is this equation. So this is ordinary conservation law. Should be? Yes, thank you. So now the two steps that we have to carry out are the following. That first, we assume that H mu nu is small enough so that, and the T mu nu is 0, the matter energy momentum tensor is 0, so that the right hand side vanishes. And then we have to solve the linear equation because we just have set left hand side equal to 0 and find the plane wave solutions. H is dimensionless, right? With the thing you have used, so H is small compared to 1 because it adds to it mu nu, right? So you just say that it's small. So assume H is small, no T mu nu, solve this equation to get the plane waves. Then think of the right hand side as source, and you solve this equation iteratively. Right? That's the way you can think of gravitational waves. Okay? This makes sense far away when H mu nu is small. Nearby, you have to basically solve the full nonlinear equation. You can write it this way, right? But at the end, you have to solve the full nonlinear equation for gravity. Okay, when particularly for black hole mergers, right? There is no escape. You have to do that. Is this clear? The strategy? Dynamics of the self-sourcing. Why? Basically, that's the equation, right? That even if T mu nu are 0, right? This will source. If you keep the linear part on the left hand side, right? This is sourcing metric, right? So this is a mathematical statement that gravity sources itself. Right? Now, why it happens? The physical reason is that the energy is essentially the source of gravity, right? And gravitational waves do carry energy. The gravitational field carries energy, right? When we started writing the equations, right, we didn't need to add explicit energy density for gravity, right? Because Einstein's equations are the complete equations. But when we rewrite Einstein's equation as something that is linear plus nonlinear, right, the nonlinear part you can think of as source of the field itself. Yeah, you can think of it as a feedback, right? If you just think of the differential equation, right, and if you're solving it for small h, you can think of this as feedback, that you produce h and that feeds back onto itself. But physically, you can think of the reason that you have h in the source of gravity is because gravity is coupled to energy and everything should carry energy, right, including gravitational field.
There are waves which completely destructively interfere.
Schwarzschild solution gravitational wave is just 0, meaning.
Yeah, but from the, I mean, if you're looking at it from the decomposition point of view, then you say that the source is
See, sources don't always produce waves. Even electromagnetism, right? A static source produces electric field but not waves, right? So Schwarzschild solution is like that. That there is a static source, but it's not, because it's not moving, it doesn't produce waves. Right? I mean, normally in electrostatics, you don't think of there being no electromagnetic wave because there is destructive interference. Right? It's just not there. Maybe you can think of it that way, but it's not very useful. Right? You can think of this Schwarzschild also in the same language. Right? So not all sources will produce waves. Typically, time-dependent sources will produce waves. Okay, except that in gravity, you have to be a little more careful because time-dependent is a somewhat vague statement, right? Even the Schwarzschild solution, you can change coordinates to make it look like a time-dependent source, right? So time dependence doesn't always produce waves because it could be just a coordinate definition.
So far, we haven't assumed any situation. It is so far very general. So even if we put the right hand side equal to 0, I wrote it. There's this first order equation that we are getting that is indicating towards a plane wave solution.
Yes. So that will give plane wave solutions, yeah, right?
Does that mean like in any situation, with there will be a gravitation? Because like you pointed out, in the Schwarzschild solution there is no gravitational waves. Does that mean this R mu one, the first order correction will itself be 0 in case of Schwarzschild?
No, you will get the analog of the electrostatics, right? See, R mu non-zero doesn't necessarily mean that it's a wave, because in electrostatics, right, you get a mu that A0 equal to 1 over R, right, Q by R. It's non-zero, but it's not wave, right? So Schwarzschild solution is something like that. The Schwarzschild solution?
Yeah, because when we put the right hand side to 0, this always indicates some sort of wave solution, right? This first order equation that you wrote.
Well, I mean, in electrostatics, right? If you ignore the delta function source, then you don't have a source, right? But still 1 over R. See, 1 over R solves the equation in the absence of source, right? But you still get some something, but you know that there's a delta function source there, right? I think the Schwarzschild is also like that, right? Except that here you have to, the feedback is there, right? So suppose you just solve the first order equation, right? R1 mu nu minus half R1 eta mu nu equal to 0. That equation that solution has to be corrected, because given that, so you get some H mu nu, right? That H mu nu has to be put back on the right hand side, right, and solved again. Okay. So if you do something like that, you will get the Schwarzschild solution, but expanded in parts of M, right? Because smallness of M is the smallness of H mu nu, right? If the mass parameter is small, then the H mu nu is small at a fixed R. So that's the way the Schwarzschild solution can be built, by repeated application of this, right? Just solution of this is not going to give the full Schwarzschild if you just solve the linear equation, right? You'll get something like 1 over R, right? Just like in electrostatics, but you'll not start seeing the horizon, for example, by solving the linear equation. Because near the horizon, H mu nu is big, right? I mean, even though we know the Riemann tensor is small, right? But in a given coordinate system, H RR, for example, H rho rho, right, has a 1 over 2m minus rho, 1 minus 2m over rho. So it blows up PR rho equal to 2m. So you have to iterate this. But all I'm saying is that not every solution needs to be waves, right? Schwarzschild is not a wave, right? It's just a static solution. Which term?
If that yellow box equation.
Yes.
If G is only eta.
Yeah. Yeah, it will go to 0 because it involves quadratic in H, right? By construction, it involves quadratic in H. If G is just eta, then that will be 0.
So that would mean that when we have cell source, so that means cell source is there a signature of some sort.
Well, that's not completely true, because if even in the absence of source, you can have plane waves, right? Which will source itself. Right? See, even in electromagnetism, you can write a plane wave solution. That's a solution without source. Right? It's just that doesn't vanish at infinity, so you put some additional boundary condition, etc. Right? So it's possible to find solution without source also, right? Even in electromagnetism. In gravity, there is additional complication that if you find a solution without source, right, you cannot stop there. You have to now ask how the source affects the gravitational field. How not the source, how the field that you found, right, the linearized solution starts affecting the field. Strength should be small, right? That's what I said. H mu should be small. Linearized solution is valid only for small h. Yeah, otherwise this expansion is not valid, right? If h is not small. That's why near the horizon, for example, if you are trying to solve for Schwarzschild solution by iterating this equation, right? You may get the faraway regions, right? In the faraway region, right? H starts with, if you take 1 minus 2m over rho, right? This of course is small deviation from 1 anyway, right? This is h00. Sorry, minus 1 plus h00 is minus this, right? This is a g00 component. And then h rho is 1 over 1 minus 2m over rho. Right? If you start solving this in the linearized version, right, what you will find is this expansion. In parts it is in m. But you can see that this expansion, as rho goes close to 2m, right? This is not a convergent expansion, this starts diverging. Right? So you cannot build a full solution by iterating, but far away you can start building the solution. Yes. Will not work. Yeah, exactly. Right? But the point is the kind of solution that we are dealing with. Asymptotically, we assume that the metric goes to each other. Right? So there the linear solution is good enough. Right? And then you say what happens as you go close in the interior, the linearization becomes there is no general analytical prescription. In special cases, you may be able to solve it. As I said, in spherical, suppose you have a spherical symmetric time dependent source, right? Here you may be able to solve it because of the symmetry that you have, right? But in general, okay, that's a nonlinear partial differential equation, right? So there's a general analytical method to solve it. I think, yeah, spherical symmetry, it will have a time varying field, right? But not waves. That's something you have to work a little to check this. No, spherical symmetry. Well, yeah, maybe say spherical symmetry is not a good thing. Rotating solution, for example, right? Rotating configuration. Yeah, axial symmetric also far away, it will be the curve solution. Okay? But you can put sufficient time variation, right? Exactly, that's right, yeah. Okay, a curve solution maybe which is rotating slowly, right? Those kinds of solutions. Yeah, so you have to find, I mean, if you want to find exact solution, right, you have to find your system, right, which you can solve, right? In general, you don't have analytic solution, right? So it's up to you to solve it, right? In fact, I mean, not only that it's up to you to solve it, right? You have to show that it's not coordinate transformation of some other solution that is known, right? In fact, this was one of the problems in the initial days of this subject, that people are writing a lot of papers, right, finding new solutions, and most of them turn out to be coordinate transformations of something which have already been found, right? So then the journal made a rule that if you want to propose a new solution, you have to prove that it's not coordinate transformation of something which is known. maybe calculate Riemann tensor, etc., and so that it's not, it doesn't coincide with not Riemann tensor, some scalars, right? And so that it doesn't agree with what the known solutions have, right? But this is something that has to be checked, right? Because you cannot, I mean, if you are dishonest, you can take a solution that you know and make a complicated coordinate transformation, right? And propose that is a solution you have found, right? Yes. This T mu nu is the matter source, yes. Yes.
But earlier we saw that this T mu is conserved by.
But with d mu.
Yeah.
Right? It was G mu nu, G mu rho, D rho, T mu nu is 0.
Now we still have this.
Yeah, this condition is still have.
Can we say, I mean, when we calculate this, we will get some partial derivative of T mu plus some reciprocal.
Exactly.
And those are sort of getting cancelled by
This one.
T graph.
Exactly. Right. So this one, for example, you can write eta mu rho plus something that involves powers of h, right? And t, right? But t, of course, you can write in terms of r, right? Because you have this original equation, r mu nu, Einstein's equation is there, r mu nu minus half r g mu nu equal to t mu nu, right? So what to do is that you take this part, you keep aside, right? Everything else where there is t mu nu, you write in terms of this, right? And then the h mu nu, etc. Yeah, up to any order that you like, you can keep, and that will agree. That will basically give you this, right? So it's not a new equation; it's a new rewriting of the old equation, right? Which makes the conservation law looks like the more flat space conservation law. Okay, any other question? Okay, so let me now give the expression for R1 mu nu. Okay, so R mu nu, let me write R1 mu nu is to be calculated by R rho mu nu. Calculate all this, and this superscript with 1 means you keep the linear term. Okay, you calculate this and then keep the linear term. So this I can write I wrote the expression for R, right? But I left out the gamma terms because those are non-linear anyway. Right? Each gamma is linear in H, so gamma terms you can ignore. Is this clear? So this one, let me rewrite this. Okay, so what I have done here is that there is a G rho sigma here. But because these are already linear in H, right, the G rho sigma I can replace by eta rho sigma. So this you can simplify. I'll just write down the result. Some cancellations. Box is eta rho sigma. Ordinary Laplacian in flat space. And most important is that from now on, we raise and lower indices by eta. Okay. So when, for example, H rho rho, right, is eta upper rho sigma, H lower rho sigma. Okay, that's the definition. Okay, we always raise and lower indices by rho, by eta. Okay, so basically the point is you have 3 terms from here and 3 terms from here. 2 of them cancel. H rho rho, yes, this one. Why is that? Okay, let's see where that is coming from. Somewhere, yeah, you see there is a eta rho sigma, G rho sigma. There is a derivative of H rho sigma, right? So that's what gives the eta H rho rho. Yeah, in fact, there are probably several terms, and 3 of those are two cancel pairwise, if I remember correctly. Yeah, in fact, these 2 cancel because this is antisymmetric in rho and sigma, right? And this is symmetric in rho and sigma. So these 2 terms cancel, but there is somewhere else where it's there. Oh, this one, right? This one is there. Eta rho rho. This box, right? Let's see where it's coming from. Eta rho, yeah, this is eta rho sigma. The derivative of with respect to rho, derivative with respect to sigma of G mu, right? That's the box H mu, right? With a minus sign because of this minus sign here.
Can you explain why we didn't del H?
Which term?
H, del H kind of terms. Here we are writing only
linear. Yeah, because R1 by definition is a linear term.
But this H del H is because can you just explain why H del H is ordered del square? Order H square.
Because there are two factors of H, right?
But again, just come back to the
Yeah. So the assumption that derivative of H is of the same order as H, right? So when I say we are linearizing, right? We are ignoring not just quadratic terms in H, but anything involves H with any arbitrary number of derivatives of H, right? Because we are thinking of H as some small number multiplied by a smooth function, right? And we are expanding in parts of that small number, right? So the smooth function, when you take derivative, right, you get some other smooth function, right? Something of order 1. So that small number, when you raise to second power, is what we are ignoring.
But when we look at the fluctuations are really
But they look large. They are actually quite small. I mean,
okay.
they are quite small, right? I mean, they look large because the gravitational wave frequency, right, is well, large means what? I mean, what are you comparing with, right? It's much smaller than the visible wave, visible light, for example, right? It's some of the order of hertz, right? That's what you see. So it's not large; it's actually small, right? Because of the order of seconds, you are taking derivative. So certainly, derivative of h is not large in any sense. When you study gravitational waves, not elsewhere, because you are taking this as a convention, right? That from now on, because I have already decomposed g into eta plus h, right? And so now when you are raising indices, it makes no sense to raise with eta.
So h rho is also eta rho.
Yes, indeed. So this is eta rho sigma, h rho sigma. That's the definition. Okay, now once you have decomposed it, right, you don't have the usual general coordinate invariance anymore because you have already destroyed general coordinate invariance, manifest general coordinate invariance. Not that you are not changing any equation, right? But manifest general coordinate invariance you have destroyed because of the split, right? Neither eta nor h are individual tensors, right, under general coordinate transformation. Okay, so there is still some relic of that we'll see, but the usual form of general coordinate invariance is not manifest anymore. So now all that we will rely on is Lorentz covariance, right? Because you are thinking of this fluctuation around the flat space background. Well, these all have h, right? Yeah. So from now on, what we'll do is whenever there is a h, we'll write it explicitly, right? If something had been raised with g, right, I'll write explicitly g as in terms of h, and write out the form for h explicitly, right? So that raising index, right, there will be no hidden h. If you had used g, right, then there will be some h hidden there, right? We want to make all h's explicit, right? So that we are sure that you have kept linear terms and everything else has gone to the other side. Okay, so with this R1, right, and so this is R1 mu nu, and R1 is just by definition eta mu nu R1 mu nu, right? So using this form, you can verify this. Right, this is a straightforward linear algebra because this is known as a linear function of h. Right? This is known as a linear function of h. All you have to do is substitute and take the derivatives, right? And so that they combine in such a way that it just cancels. Okay, as I said, this is a consequence of the fact that initially you had the Bianchi identity, right, with covariant derivatives and g, and because that was an identity, right, it's valid for every g. We could expand in powers of h, and it should order for every order in h separately, right? It should work for every order in h, and this is the leading term in that identity. Okay, but once you have this, we can explicitly check this also. Is it clear? So now we have to solve this, right? So let me do a few more steps and then we'll complete it next time. Yes.
This won't be true if H is not.
Well, we have not even discussed what the original general coordinate invariance is, right? See,
You just said this for the Bianchi. This is basically the first order.
yeah, see, Bianchi identity is an identity that involves only the metric, right? Okay. So it holds for all H, right? If you write G mu nu equal to eta mu nu plus H mu nu, it makes no difference, right? It holds as an identity. Now, if you have an identity, then you can expand it in parts of H, right? And it should hold for all H. So that means every part of H should satisfy that.
So I will ask you whether this will it is not.
This is an identity, right? Once you have written that equation, right, it makes no difference if H is small or not, because it's only linear in H, right? What you can say, that equation is relevant when H is small, right? But as an identity, okay, you just substitute this form for H. Why did it go there? That R1 mu nu, right, which is given as a function of H, substitute there, and it is true. You can explicitly check that this is valid. Right? What you are saying is that the fact that this is a meaningful exercise, right? R1 mu nu, right, is physically meaningful only when H is small. That is true. Right? But as an identity, it holds for all H. Is this clear? Okay, so the form of the equation that we're going to solve is a little simpler version. So we are still in step 1. This is what we want to solve, right? Because you are ignoring nonlinear terms and the source terms. So this, if you multiply by eta mu nu, okay, and contract, this tells us that R1 minus half R1 times eta mu nu is 0, right? So this is 4. So that tells us that minus R1 is 0. Okay. So we can just solve. R1 will be equal to 0. Okay, this is what we did also for the Schwarz side, right? Except that there we had done this manipulation with G mu nu, right? Because we didn't want to make a linear approximation. Here it's already linear, right? We just contracted eta mu nu and subtracted this. So that means you have to basically solve that equation. R1 mu nu expression is given there, but it has gone behind. Okay. So let me write that equation. So you need to solve. So I can call this rho. So that's what we had there, right? So is this clear? So this is the analog of Maxwell's equation. right? Linear del mu j f mu nu equal to 0. That's so this is analog of that, right? But now if you recall, for electromagnetism, right, we also have to choose a gauge while solving it, right? So you have to also choose a gauge here. Now to say that you have to choose a gauge, we have to first check that there's a gauge invariance, right? For Maxwell's equation, there's a gauge invariance, right? So we have to first check that there is a gauge invariance, and then we'll choose a gauge. Gauge invariance of this equation, same, okay? But it will be induced from general coordinate invariance, right? We can of course directly check that this equation has that gauge invariance, but we'll try to get the gauge transformation law from general coordinate invariance. Now the problem is that if we start with, suppose you are taking an arbitrary general coordinate transformation, then if you start with the metric eta mu nu, it will go to something quite different from eta mu nu, right? Under an arbitrary general coordinate transformation. Okay. So it will not be close to eta mu nu, right? So you cannot say, okay, this is the amount by which h mu nu changes, right? Because if you make a big general coordinate transformation, you will get a big change in G. So we have, in order to think of a general coordinate transformation of H, we have to make sure that the gauge transformation parameter that you are choosing, right, or the general coordinate transformation that you are choosing, is also small in some sense, right? Small in this case means it should be close to identity. It shouldn't be too much change, because if you make a big change, right, x to x prime, which is a complicated function of x, right, then it is going to take away from eta mu nu by a finite amount, right? You cannot interpret this as a change in h mu, because we are working on an approximation that h mu nu is small. So what we do is that we use a version of general coordinate transformation. It's a special case, okay, where the transformation is close to identity. So we use general coordinate transformation x prime mu, because we have x mu plus and this we assume to be small. Now I use the fact that g prime mu nu of x prime is and I'll leave it as an exercise to prove that g prime mu nu of x minus g mu nu of x is, I'll take this through minus sign. Okay, so there's a minus sign hanging around there, but it doesn't really make a difference. This is ignoring terms of order xi square or h square or h square or xi h. Because you think of xi, the transformation parameter, as being of the same order as h. Okay, so that yeah, but I have to write G mu nu as eta mu nu plus H mu nu. That definition remains the same.
The right hand side is lowering and upper is raising.
Yeah, with eta, everything, right? So from now on, as I said, we raise and lower everything in eta unless I change it. And this is eta mu nu plus H prime mu nu. Okay, this one you may remember that we had once earlier found this infinitesimal transformation of G, right? But there is a covariant derivative sitting here. Okay, it was a covariant derivative of psi plus covariant derivative of psi. Okay. But the covariant derivative and the ordinary derivative differs by terms of order h. Right? So you'll get some h times I, right? Those terms you are ignoring. Is this clear? So this means that gauge invariance is h mu nu goes to h mu nu plus this is what general coordinate transformation tells us, but a special kind of general coordinate transformation or the transformation parameter is of the same order as h. Okay, because if you make it much bigger, then the new metric will not have the form, but you can think of this as eta mu nu plus something small. And now I'll leave it as an exercise to check that this is a symmetry of the equation. Okay, again, it's more or less straightforward because it's linear equation, right? All you have to do is to check that if we substitute for h mu nu, this shift, all these terms will cancel each other. Right? So that's the sense in which this is a symmetry of the equations. In a sense, it's guaranteed because Einstein's equations are invariant on a general coordinate transformation. Right? And all you are doing here is that you are linearizing Einstein's equation and linearizing the general coordinate transformation. Okay, so next time then we'll start from here, the equations of motion and the gauge invariance. Okay. Now you have to carry out the next step, which is to gauge fix and then find a solution. Okay, so I think I'll stop here. Are there questions?
One question related to last step. So I was just thinking, suppose you take the right side interaction, R time square root of G, square root of G.
Yes.
Try to find the Noether current due to translation.
Yeah. Oh, the problem is that because the translation symmetry is gauged, okay, the standard Noether procedure will not work. Right?
Because it holds true for local.
Exactly, because it holds for local transformation. Right? The application of the Noether procedure when the symmetry is local is a little subtle. I mean, you can still do it, but you have to do it in terms of the asymptotic geometry, right? You have to look at some transformation which doesn't vanish at infinity, and based on that, you have to find the expression for the energy or energy momentum tensor, for example.
So similarly, electrodynamics, so suppose it's shifting E, like mu going to plus, which is also a subset of the.
Yes.
There also we should find the Noether current.
Yeah, local, that standard analysis will tell the Noether current is 0, right? But if you do a more careful analysis, you will find that the Noether charge is just, there's a current, but there is a charge, right? Which is the integral of electric field at infinity, right? That you know is the charge by Gauss law. So similarly, you will get an expression for the energy, for example, but as an integral at infinity. Yeah, it is meaningful. That is what is called the ADM energy. ADM, right? And that's the definition of that's the energy that an observer will see from far away.
let us know that some of you had written some feedback that you're finding something difficult. So, I mean, if you have anything that you want us to discuss, please let me or Ravi know.
So next week, the Thursday's class will be a tutorial. So if you have any difficulty, just catch one of them.
So we are planning to
Either in the tutorial or outside the tutorial.
Sure, yeah, please. So we're planning to discuss the first assignment. We discuss solutions from there. But if you think something else must be discussed, then
So if this transformation is used, the Maxwell equation stays same.
Yes, indeed.
Here, gate invariance means that if this transformation H mu
This equation will remain the same.
this will remain nothing will cancel out. And
Exactly. So the extra term, right?
Yeah.
See the extra term, if you replace H mu by this, right? You'll get some extra terms on the right hand side, on the left hand side, right? All those will cancel out.
so everything will just go to some primes of H.
Exactly. So if H satisfies this equation, right, then H prime, right, which is this, will also satisfy that equation. Right? That's the statement.
That is what you
Yeah.
check that.
Exactly.
So I had a similar question. How do you know that this is the most general transformation?
Well, this is the most general transformation which is close to identity. You may get some accidental symmetries, right? Which is big. The point is, okay, if you take eta mu, right, and make a general coordinate transformation that is big, right, where x prime mu and x mu are not close, generically, it will not remain close to eta mu, the metric, right? And so you cannot interpret this eta mu plus h, the small h mu, right? So that's the sense in which this is the generic, right? It may happen that the original theory had some symmetry. Original solution had some symmetry, right? That's the solution that which you are trying to do, and you can try to make that transformation, right? Like eta mu has a Lorentz symmetry, right? So if you make a Lorentz transformation, right, it's going to change eta mu to itself, right? So that will also be a symmetry. But that's not what we call a gauge symmetry, right? The Lorentz symmetry will be the Lorentz invariance of this equation, which is manifest here, right? So indeed, those will also see, right? It's manifest here, and you can check that if you make a big change, right? Lorentz symmetry doesn't have to be infinitesimal, right? Make a big Lorentz transformation, eta mu remains eta mu, so you can still interpret this as eta mu plus some h prime mu, right? And that is also a symmetry of this.
But under some Lorentz transformation, H may not be.
Well, when I say remain small, that means that if it goes to a multiple of h, right? See, high boost factor, you can ask that question also for Maxwell, right? If you give a high boost, the Maxwell fields may change, right? May get a large amount. But you can always fix the amount of boost. You can always take sufficiently small a or small h where it remains small. Right? So when you're talking about remaining small, right, you can also think of it parametrically, that you put an epsilon in front of h, right? You write g mu as eta mu plus epsilon h mu, and you want to what to first order in epsilon. Exactly. Yeah, we haven't defined how small epsilon is, right? Exactly. Yeah.
And here also we are all this, and it manifests the fact that we are considered the linear.
Exactly. That's right. Right. So because by ignoring this, you can guarantee that it's a symmetry of the linear equations. Right. The full symmetry is of course more complicated, right? On both sides. I mean, on the symmetry transformation will have higher order terms, and this equation will also have higher order terms. But right now we are just looking at the linearized equation, so you have to look for the symmetries of the linearized Einstein's equation.
If we split the G mu, but G mu will transforms like general tensor.
Yes.
And eta mu transforms like Lorentz tensor.
Exactly.
Then how does like since you just mentioned that this is Lorentz invariant equation.
Yeah, so H also transforms as Lorentz transform, right? Because G, you can look what from the transformation of G, right? G goes to another Lorentz transformation. G goes to lambda G lambda transpose, right? And lambda eta lambda transpose is eta, right? So H prime basically becomes lambda H lambda transpose. Right? So Lorentz transformation also you can think of as a part of general coordinate transformation, right? But those are not gauge transformation, right? Those are rigid. They don't have X dependent parameter. The point is, if you want the parameter to have arbitrary X dependence, right, then this is the kind of small transformation you have to make. Right? And those are the ones which are analogous to gauge symmetry, right? That this allows us. Well, quantum, okay. See, non-linearity is not, at least, not a priori the stumbling block, because there are many nonlinear field theories that we have quantized, right? Like standard model, for example, right? Strong interaction, electromagnetic is linear, but strong and weak interactions are non-linear. Right? The main problem here is that the number of derivatives that the action has, right? There's a dimension full parameter, expansion parameter, and that makes it hard to quantize. Right? It's not visible just at this level that you have worked on, but once you start doing loop calculations with these, right, you find that loop calculations are much more divergent than in electrodynamics, for example. Exactly. By renormalization, by the standard procedure of renormalization that you do in electrodynamics, in quantum electrodynamics. But that's not easy to see based on just what we have written so far. Exactly, yeah. Okay. So the effective coupling of gravity is dimension full, right? Which is not the case for electromagnetism. Well, no, it doesn't go back to self source, right? Of course, everything is connected, but because self source, as I was saying, the strong interaction fields are also self sourcing, right? That's also nonlinear, but you can quantize it without any problem, right? It's renormalizable. So it's more than having just self sourcing, right? It's without self sourcing, of course, the equations will be trivial, right? But even with self sourcing, there are examples of theories which are renormalizable, right? Here, the reason that it's not renormalizable is because of this fact that there is a dimension full coupling, right? You can say that in electrodynamics, the source is a charge, right? Here, the source is energy, right? And if you have particles colliding at very high speed, right, high momentum, then the energy can be increased, right? Whereas the charge is kept fixed, right? So because of this, at high energy, gravity becomes stronger and stronger, right? Which is not the case for electrodynamics, right? And that you can say is the reason for this additional difficulty, right? Because in the loop, as virtual particles, there is always a high energy process going on, right? Arbitrarily high energy process. And those processes are much stronger for gravity than for electromagnetism. No, no. There is a change, there is some running, some change in the effective coupling, but that's logarithmic. Right? Whereas here, if you go to high energy, right, the interactions are quadratic in energy, right? Just Newton's law, right? GMM, that M gets replaced by energy. And that, so that this growth, right, is too uncontrollable for the usual quantity.
without even calculating, then we decompose the metric as
Yeah, you can, because the point is that imagine that you have some function of x, which is 0. Say f of x plus g of x equal, or maybe f of x square plus g of x. Now we expand this out in parts of x. Every part of x has to vanish. True, but you just think of this g as coming plus epsilon times h.
this is not true. Why this is not true?
No, because
You may not
this
know.
basically means that derivatives of h you are counting at same order as h.
Yeah.
So when you calculate d right?
Yeah, if that is not true, then this is true.
So then it will not work. By definition, EN is something that involves n parts of h. Irrespective of whether the sum of those n is some kind of derivative. And the definition, as long as you define EN that way, and it has n parts of h or its derivative, then this is true. Then this works. You could drop some derivatives, like saying that okay, those derivatives are small.